Alright, welcome back. Multiplying and dividing radicals. And, oops. Unlike adding and subtracting, right? When we're multiplying, we don't need like terms. And that's, again, why multiplying is kind of nicer or better than adding and subtracting all the time. We can multiply anything. We're going to multiply if I had square root of 50, square root of 5 times the square root of 10 would equal the square root of 50. So if I multiply those together, I get root 50, and then after I multiply, I'm going to simplify. So if I simplify that, I do square root of 25 times 2, and that would be square root of 25 is 5 root 2. But if I go ahead and look at that, before I multiplied, right, if I think about, well, what's the square root of 5 times the square root of 5? Now, some of us are going to say, well, that's the square root of 25, which is 5. But again, a lot of us are going to say, oh, square root of 5 times the square root of 5, that's like the square root of 5 squared. And these two things, the squared and the square root, cancel each other out. Right? So this is just the number 5. You can make it root 25 and then simplify it, but you can kind of shortcut and jump it. Anytime you have two like radicals that you're multiplying together, it becomes a whole number version. And so when I take a look in here, all right, there's a root 5 here. This is really root 5 times 2. So this root 5 with this root 5 becomes the whole number 5, and then the root 2 is the unlike radical that has to stay in there. Now, same thing with this one. Root 3 here, root 12, you can multiply it to be root 36, which is 6. Or you can see the root 3, and this is really root 4 times 3. So the root 4 is 2 times the pair of root 3's is 2 times 3 or 6. If I'm going to go ahead and multiply two radical expressions, 5 root 2 times 8 root 8, I multiply the whole numbers times the whole numbers. And then the square roots times the square roots. So 5 root 2 times 8 root 8 is 5 times 8 or 40. Root 2 times 8 is 16. And then I'd simplify. Once I multiply, I need to make sure that I simplify. 40 root 16 is 40 times 4, which is 160. And there's no square root left. Okay. So again, we see that we're looking for, if we can either multiply it to be root 50, or we see the pair of 5's in here. And this is 5 times 2. So the 2 is kind of by itself. The two root 5's become 5. And then the root 2, the lone radical, stays inside. Another way to think, look over here, another way to think of square root of 5 is 5 to the 1/2 power. Those are the same thing. And if I multiply 5 to the 1/2 times 5 to the 1/2, like basis means I can add the exponent. So this becomes 5 to the half plus half is 1, or 5. Root 18 times root 36. I can multiply these together to get the square root of 648 and then try to simplify that. The smarter way to do this is to see, this is, root 18. There's an 18 in here. I would like there to be, and there is. This is 18 times 2. So root 18 times root 18 times 2. This part is going to be 18, and then there's still root 2. Now I could maybe see that and see that this is 18 squared, which happens to be, what is that? 2 to 56 to 89, 324. Yeah. So this is 324 times 2, and the square root of 324 is 18. Now, maybe I didn't know that. Maybe I did know that. I might divide it by 4. I might divide it by 16, depending on what I can. But square root of 324 is 18. This is the easier way to see it, right? The easier way to see it is see the pair of 18s in there. The square root of 18 to the square root of 18 would become the whole number 18. Now, we take a look at this one. Root 6 times root 10. There's not a pair of any, but there is. There's a pair of 2's, right? This is 3 times 2. This is 5 times 2. So the root 2's, let's get a pen here. All right, root 3 times 2 and root 2 times 5. The square root of 2 and square root of 2 will become the whole number 2, and there's a 3 and a 5, or root 15 left over. Now, again, the simpler method, but a little longer, would be make this root 60 and then simplify it. It does simplify it down to 2 root 15, but if you can see the pair of, if you can see the pair of 2's in there, and what's left stays in the radicand, you're good. Here, there's a pair of root 5x's. So root 5x here, and this is root 5x times 3. So the 5x is going to come out, and the root 3 will stay in. Ta-da! Lesson here, root 2 becomes 2. 4 times 8, that's 8, and that's a 6 positive. 8 times 6, 48, times the 2 here is 96. Yeah. Alright, I want you to do these 3. 1, 2, 3, and pause it. Come back when you have answers to those. Okay, for number 1, did you make it 2 times 12 or 24? Number 2, did you see the pair of 5's? It's root 50, which is 5 root 2, or you could see the pair of 5's roots, which becomes 5, and then there was a root 2 left over. Same thing with number 3. Did you make it root 98 and then re-simplify it, or did you see the pair of 7's and then the root 2 left over has to stay in the radical? 2x, is there 2x in here? Sure, this is root 2x times 3, so the root 3 is going to be left over, stay in, and we're going to get 6 times 2x becomes 12x. What's the pair? There's a pair of root 5y's. This is 5y times 2, so the root 5y and root 5y in here becomes 5y, so it's 4 times 6, or 24 times 5y, and then the only root that's left that's not used is a 2, and so then 24 times 5 becomes 120y root 2. Alright, now we're going to move into a little bit of division. Again, the argument still stands that division doesn't exist, it's the inverse of multiplication. But what I'm going to do here is root 20 over root 5. I'm going to break up the 20 into root 5 times root 4. And the root 5's are going to cancel. So this just leaves me with root 4, which is the whole number 2. We want to simplify it as much as we can when we can. Woo! So what's this? You could say it's root 630 over 35. Right? I see a root 7 here. And this is really root 5 times root 7. So the root 7's can cancel. Alright, and then I've got root 5 and root 90. There's a root 5 in both of those. This is 5 times 18, I think. So the root 5's will cancel, and it just leaves me with root 18, which is 3 root 2. Now, if you just multiply it across at the beginning, you get root 630 over root 35. And if you divided it out, 630 is going to be 35 times 18, I would bet. So you can just do the division here, but you want to make sure that you're canceling out. The last thing I want to talk about here is something called rationalizing the denominator. Math people have a problem with this because 2 root 15 divided by root 2. Dividing by what? Well, root 2 is an irrational number. It's a number that doesn't end and doesn't repeat as a decimal. So how can we divide by it? And we have a very difficult time doing that. So instead of dividing by that, what I'm going to do is I'm going to multiply the top and bottom by whatever is in the denominator, what radical, in order to get a rational number. So if we multiply the top is going to equal 2 root 30. And the bottom is going to equal root 2 times root 2 is root 4, or the number 2. And lo and behold, the 2's will cancel. And root 30 is my answer. Now, do I leave it like, do I leave it like root 30? Yeah, it's not a perfect square. No perfect squares go into 30, so we have to leave it like that. Alright, last one I want to do is I'm going to rationalize this denominator. I can't divide these, they don't come out evenly, so I'm going to multiply both sides, top and bottom rather, by root 3. This is the mass 1. Alright, root 3 times root 3 from our discussion today becomes 3. And 6 root 15. And I'm going to be able to cancel here. And this often happens. Alright. So it gives me 1 and 2. 2 root 15. That would be my simplified answer. Alright, I think that's going to be it. End of section. Thank you very much for watching. We're going to be practicing these computation of radicals in class. Namaste.